everyone, and welcome to the first Spinnaker Community Forum for 2021. I also extend a welcome to the more than 300 people who are joining us on live stream from home. I just ask that because the internet can sometimes be a little temperamental, can I ask people here in the audience to turn off the Wi-Fi on their phone and not access any internet during the presentation and Q&A so as to not interrupt the connection and drop out from home. I also remind you that a link will be provided to this presentation if you should like to share or revisit afterwards. So please keep an eye on our social channels and also communications that will be sent directly to you with the link. I acknowledge that we meet today on Murdoch, traditional lands of the Noongar people. I recognise and respect the longevity of their culture and the continuing contributions they make to our community. I pay my respects to the elders past, present and emerging. Spinnaker holds these community forums throughout the year to ensure the important research we fund is translated directly to the community, as we believe it's critically important for us all to be aware of exceptional outcomes in medical research. But we also think it's incredibly important that you're aware of the opportunities that may represent to you and for your health. This forum is perhaps even more critical for us all, even from the safety of Western Australia. Today significantly marks the precise anniversary of the sudden and enduring closure of Australia's borders due to the calamitous and poorly understood threat of SARS-CoV-2. As of this morning, there were 2,712,628 reported deaths from this virus. And that's from 122,869,331 known diagnoses. Daily reported cases remain above 500,000. Yesterday, 89,000 Brazilians were diagnosed positive. Overnight, 2,730 people in Brazil died. This is just what we know from reported data, and there remains uncertainty globally as to how accurate the testing and reporting of the virus actually is. But there's another significant number I want us all to consider. Of the more than 122 million diagnosed cases, just over 99 million are reported to have recovered as of today. About a year ago, Professor Jeremy Nicholson and I met in his office at the Australian National Phenome Centre, and we discussed this very thing, recovery. We ruminated on the notion of recovery and asked a very important question. What if you don't? What actually happens when you're infected? And what does that mean long term? 1 year later, we have a pretty startling set of data that tells us you may not. Jeremy and his team have now published multiple papers internationally based on data collected from samples here in Western Australia and sent to us from across the globe. Research that is leading the world. And papers that number in the top 3 read COVID research publications in the esteemed Journal of Proteomics Research. This is an exceptional opportunity for you all to hear from one of the world's most respected scientists. And at the end of his presentation, I will welcome questions. Please join me in welcoming Professor Jeremy Nicholson.
Okay. Make sure this doesn't collapse horrendously. Madam Chairman, ladies and gentlemen, thank you for that kind introduction. And indeed, it's been an extraordinary year, I think, as everybody knows, and everybody has been impacted by this pandemic in a variety of different ways. So I just want to start off by giving a little bit of background about how we got into this and why, and a little bit about our laboratory, the Australian National Phenome Centre at Murdoch University. So I spent the last 20-odd years prior to coming to Australia as the head of a big clinical department in London at Imperial College. And we also set up a phenome centre there. A phenome is basically an expression of your gene and environment interactions. It allows you to study the origins of diseases and how they impact on you as an individual. And it's when we basically set the lab up, or we're setting it up, and it was opened officially on October the 4th in 2019. And we're getting ready to start doing some interesting projects and getting funding in, and then COVID-19 appears. And it becomes the most important thing to do in the world, and for reasons that I'll explain. And our lab was built for tearing apart difficult diseases. It was built to understand the unknown. So it was a hell of an opening for us to start with COVID-19 in any case. So a lot of what we do is about understanding the chemistry of life, and in particular how genes and environment interact. Your genome is your blueprint for life. And this is how Francis Crick said that. So basically it's a set of instructions on how to build an organism. And there's variation in that because that allows evolution, and it means we're all a bit different. And it also means that every now and again there are variations which can cause diseases or affect our susceptibility to diseases. So a lot of the background of our, shall we say, susceptibility is built on your genomic core. But how you're exposed to your environment through life, and it actually before you're born, also affects the diseases that you can get. And all the things in the environment, that includes the food we eat, the drugs we take, the pollutants that we're exposed to. We call that the exposome, the things that we're exposed to. And the conditional interaction creates these so-called disease risk factors. And out of these interactions, which are partly mediated by microbes, so your body is covered in microbes, your guts are full of microbes, and they're the interface between environment and us. And out of all that complexity emerges something called the phenome. Those are all the measurable properties of your body. They can be physical ones like your height and your weight. They can also be the chemistry of your blood cholesterol level, your protein levels, your albumin level, your urinary creatinine. All the things that doctors measure are what we call phenomic parameters. And every single one of us is actually different with respect to those parameters. And when we get a disease, they change radically in ways that we can measure using advanced chemistry. So when we put the Phenome Centre together, we wanted to think about not just disease and the origins and the diagnosis of it in real patients, but we wanted to think about the totality of the environment. So our strapline was the understanding human biology and disease risks in the total environment. And actually Murdoch's a really good place to do that because it's got a big environment institute, it's got a big future foods institute as well. So we had all the bits to make a really relevant new type of Phenome Centre. And it turns out that a lot of things that we put in together to study disease risks and disease evolution actually incredibly relevant to understanding COVID-19. So a lot of the stuff we do, there's going to be some slides that I show you a bit scary looking, but don't worry about it because I'll take you through, right? But a lot of the stuff we do is based on advanced chemistry, measuring the chemistry of the body using advanced chemical instrumentation and then doing advanced mathematics on all the different patterns. But all that technology can be deployed in two different ways with respect to a clinical group of patients or people. We can look at populations of people. We can take urine samples or blood samples from them and look at all the chemicals in them and try to relate that to disease risks. So at the moment, for instance, we're ploughing through 4,000 samples from the Bustleton study, which I think is a very well-known epidemiological study in Western Australia. In fact, Australia was really good for epidemiological studies in general, and there's quite a few really important ones in WA, which is one of the reasons that actually encouraged us to move out here. So what we're looking for is something like, say, in your urine that says you've got a stroke risk that might be important in 5 years' time. Is there a signal in there that's giving away the future? That's one level, that's understanding the population and disease risks, and that's to inform future healthcare policy as much as anything else. When we come down to disease people, we need to be working on a different timescale. We need to be working on the clinical timescale for medical decision making, and that can be anything from seconds, in the case of surgery, cut something out or not cut something out, that is a second-to-second decision that surgeons make, to maybe hours in the case of understanding chemical pathology diagnostics, and possibly a little bit longer than that. But it has to be relevant to the clinical decision-making schedule. And we call that clinical phenomics. That's when something is wrong with you, and we're trying to find out exactly what's wrong with you and create new diagnostics and new prognostics on the appropriate timescale. So the same technologies and mathematics can be used for these quite sort of different purposes, which makes it a very powerful laboratory setup. So one of the things we developed when we were at Imperial is the idea of patient journey phenotyping. So following how your body chemistry changes through time under therapy, right? So what should happen, from a biochemical point of view, you should get better under therapy if the drug is working or the treatment is working. So we can monitor people, looking at their blood or their urine on a day-to-day basis and actually create mathematical models for whether or not you are doing better or potentially even worse. And this is also relevant to clinical trials where we've got novel therapeutic agents and we want to know who are good responders and who are bad responders to this new drug or therapy and understand why. So this is actually a very important concept, and it's scalable to any sort of disease and applicable to any sort of disease. These are just some of the major That's an interesting noise. Oh, we're going into Panavision now, apparently. So it's scalable and translatable, the idea for anything. And of course, that includes COVID-19, its evolution and what it does to the human body. The birthplace of the Australian National Phenome Centre actually occurred in Doha, believe it or not, where we announced the creation of an international Phenome Centre network, and David Morrison, the Deputy Vice-Chancellor, was there, and he signed up Murdoch University to that. I didn't know at that time I was going to be here, but we were very welcome to have Australia on board. So it had a major sort of press release and opening of the international network, and we became part of it then. And in fact, it was originally centred at Imperial College London. Since I moved here, it is now centred in Australia. And so we use an Australian-centred map, of course, to illustrate the different partners around the world. Then came 2020, actually really 2019, COVID-19, and the start of the major outbreak in China. Now, there's a lot of dispute about whether it really was in Wuhan in late 2020 or whether there was evidence of it being earlier. But the important thing is this, is the epidemic, the pandemic that we know now definitely did come from Wuhan, whether it was there before or not. And of course, what happened was in the early stages, it grew exponentially, very, very quickly, mainly in China. And then as soon as it got out, it started to rage across the planet. Now, America always likes to be top in things, and it became top in COVID-19, which is not a good thing to win at, and has remained so ever since, right? Mainly as a result of political indecision and political wrong decisions rather than anything else. The science in America is extremely good. The healthcare is actually very good, so long as you are wealthy enough. But the political problems are, as we know, have been very difficult. And in fact, that's one of the problems about this virus. The virus loves political indecision. It loves dissent. It loves people who don't play by the rules, because it's a tricky thing. It doesn't know, right? It doesn't know that we are, as humans, are naturally sort of disruptive, okay? So if you're not wearing a mask and the virus is there, you have a much higher chance of getting it. But the real reason you wear a mask, of course, is not to pass it on. And of course, we can talk about that for ages, about America and why it has such high rates. So the International Phenome Centre network had aspirations for tackling all the biggest diseases in the world, because we have all these different sites, all with powerful research laboratories and powerful universities. And what better than to have them all collaborating using the same sort of instrumentation, the same mathematics, so that you can combine your data and make everything much stronger. So if you look down that list there, diabetes was actually probably the top of our list for things to get together on, but COVID-19 went straight to the top of the list early last year. And we've used the power of that international community of scientists to gain access to samples here in West Australia that we wouldn't have access to otherwise. So we could therefore apply our enormous laboratory and its capabilities to tackling the problem, even though, thankfully, Australia's had, and Western Australia in particular, has had low rates. So, the international response, which is led by the ANPC at Murdoch. So we've managed to create one of the most diverse and comprehensive data sets in the world and sample sets in the world. We've got a COVID-19 import license, which is a bit of a strange thing to have, so everybody's going to keep it out. But under quite strict biosecurity regulations. We've brought in samples. To be honest with you, blood plasma samples are not very infectious unless you smear it all over your face, which is probably not a very good idea. But it's actually an airborne virus, so it's difficult to catch from liquid samples. But we now have thousands of samples from around the world using all the standardized analytical technology to create new data solutions to help us understand the problem. And there's some of the universities that we're working with. Cambridge University, we have their collection. We have a most fascinating collection just arrived actually only a week or so ago at Harvard Medical School, the pediatric collection. Pediatric COVID is a very serious disease, and I'll come back and talk a little bit about that later on. So we're in a beautiful position scientifically for solving a lot of important problems, given the background of the racial diversity, ethnic diversity, and the environment diversity, which affects the expression of the disease in different ways around the world. So, everybody in the planet has become a virologist in the last year, so everybody knows something about COVID-19. But let's just say a couple of things I think are important that we know. It's a beta coronavirus, so there are a number of those around. We think that the CoV-2 is from bats. Bats typically carry about 600 coronaviruses, almost nothing of which is known about most of them, and many of them could become future human pathogens if they do that so-called leap from species to species. It's very like the original SARS-CoV-1 virus. That's the closest one, which is also a mainly respiratory disease, but it does cause, SARS-1 caused other effects as well, systemic disease, and I'll come back to that. At the moment, we are going through an evolution of the virus. In fact, the evolution started from the first time we saw it, and there were multiple variants already had been detected by February last year. So over a year ago, there had already been 30 detected variants. So a variant actually is a combination of genetic modifications. A single genetic modification is a mutation. A variant is a series of them. And I think things like the B117 virus, the British one, which people were, so-called British one, which people were worried about, that has about, I think, about 17 different mutations in it in comparison with the earlier strains. But the point is that when you've got populations which have got a large number of people with the virus, that drives mutation. And so there are many variations out there, variants out there that we haven't even scanned yet because we can't screen everybody for the genetics of the virus. So the worrying thing is that some of these have different infectivity. So the British one looks as though it's at least 70% more infectious, 60 to 70% maybe, more infectious than the previous variants. There's also a South African variant, which is more infectious as well. And then there's numerous other ones. But the other things we don't know is, even though that we know about infectivity, we don't know about the length of infectious time period. So when you get a modification in the biology of the virus, you could be infectious for less or more time. We actually don't know very much about that yet. And that has implications when you're thinking about testing, right? Because if you know how long the incubation period is for something and you know how long somebody is infectious for, you can design a test around it. But if that's changing, then there's a potential problem. Biosecurity could get weaker as we go forward with new variants that are coming around. Now, Donald Trump said it was a bit like a flu. Well, it's about 40 to 60 times more deadly than flu, so it's not like a flu. And it can also affect every system in your body, so that's not like a flu either. It can also be passed on asymptomatically, right? Normally when flu is infectious, people are coughing and spluttering and you stay away from them, right? But in case of COVID-19, you may not show anything and still be infectious. The incubation time, typically about 14 days, but possibly longer. There's some cases now that have been shown maybe at least 21 days. So again, that has implications for biotesting if you don't understand that. And we don't really understand that properly for some of the new variants. So it's a complex multi-organ disease as well. There's almost every organ in the body can be affected by this. And not all of those yield symptoms either. And also recovery, as Dan just said. Incomplete and partial recovery is common. The so-called long COVID is the name that people have given this, or long COVID syndrome. We like to call this post-COVID syndrome now. It's a little bit more scientific. But also post-COVID syndrome is not like just a long version of the disease. It has different medical and biological features, which I'll come on to in a moment. So some statistics, Dana quoted some. I think my statistics might be an hour later than yours, so it's changed. It really just, I mean, I've given quite a lot of talks on this, and I update this slide every time. The last talk I gave, I think when Spinnaker was that October, was it November? It was 66 million then, so it's nearly doubled since then, gives you an idea. The 99 million or so recovered may not be. In the case of the original SARS, something like 50 or 60% of people had systemic disabilities and dysfunctions 12 years after actually the acute phase of the disease, 50 or 60%, right? That only affected 8,098 people in the world, SARS-1, okay, the original SARS. This is now 123 million, pretty much. So if it's anything like SARS-1 in terms of long-term effects, we have tens of millions of people out there now who have got post-COVID syndrome, and many of them may not know that. I hope that is not correct, but unfortunately the statistics that we're now starting to see look as though it might be so. Looking at gender, right, originally people were saying it's mainly men, old men get it. Well, that was true in China. Actually, as it went west, it became less true. And in fact, much wider range of ages can get it. And there is a slight preference, if you like, for male over female, but it's pretty equal. Children under the age of 10 generally don't get it, you don't see it, but they may be carrying it, right, and just not affected in the same way. The important thing to remember is the older you are, the more likely you are to die or get serious complications. So although you can get it at 30, you're much more likely to die if you're 70 or 80. If you look on the bottom left, there's the distribution of daily cases in Australia. Unbelievably, blessed by not being hit with this enormous burden that everywhere else has had. So there are two surges. But the maximum number of cases a day was about under 750. If you look at America, which is on the right, you can see there's three waves. There's some wiggles in the right-hand one because of Thanksgiving, because of New Year, and because of Christmas, right? That actually doesn't affect the rate of infection. It just affects the rates of reporting. And it looks as though it's going down very nicely, except when you bear in mind that they're still getting 60,000 people a day infected. And in fact, if you work the statistics through and how many people are being infected, it's actually 7 people a second are being infected on this planet. And 1 person every 8 seconds today is dying of this. So it hasn't gone away, and it's still very dangerous. So think about Australia. Look at the first wave, and we got it down. It was down to almost nothing, and then another wave, right? And again, if you look in America, there was a wave, it went down. Second wave went down, then because of political things around the election, let's open it up, it doesn't really exist, then you've got much bigger responses. But if you look at the numbers in America, even at the moment, it is like 80 or 90 times the highest rate it was in Australia. So opening up America now is a total disaster, totally disastrous idea, and we will see a 4th wave in the United States. Unraveling what the complexity of the disease has been an interesting task. It's mainly classified as a respiratory disease, and that's fairly obvious. People die a lot of the respiratory complaints. That's the main cause of death. And it's also the most obvious. People are coughing and spluttering, and they can't breathe properly. There are multiple stages of the disease, and most people, vast majority of people, stay in what we call stage 1 or stage 2, where there's actually not very much effect. The majority of people in West Australia who got this were actually stage 1 and stage 2 people. A relatively small number of people end up being on critical care and being intubated. So it's been looked at very much from a respiratory disease and a virological point of view. But if you then start to see all the complications or the other manifestations of the disease, which are on the right-hand side, you realise it's much more complicated. There's a lot more going on under the hood. And so it causes microembolisms, just miniature blood clots, block off blood vessels. You think about that, well, there's blood vessels throughout your whole body, so that in its own right could have multiple organ effects. There are early GI symptoms. The gut, we know, contains a lot of the virus in the early stages, and that's why you can use sewage testing to see if the local community has still actually got the virus. Right? It's a way of picking it out at a sort of geographical scale. Dyserythropoiesis, that just means failure of production of red blood cells in the liver. Porphyria is a disease that is associated with that. It's actually a liver disease, rather nasty. Liver dysfunction is very common. About 77% of patients have some sort of liver dysfunction, which does not always recover. Okay, I'll talk about that later. New onset diabetes. So diabetes has been recognised as a risk factor, i.e. if you've got diabetes, you are more likely to get a severe effect of the virus, but there's now significant evidence it causes new diabetes. Right? And one of the things that we do not need in the world at the moment is something to accelerate diabetes, because it's already out of control. And within 10 years from now, 40 million people on this planet will not have enough insulin. There's not enough production capability for the number of diabetics there will be. So we do not need to accelerate this process. And so when we start thinking about the long-term COVID, we have to think not just of the health of the people, we have to think about the long-term economic burden on the country, which can be potentially massive. The United States faces $1 trillion burden already going forward over the next 10 years. It's just extraordinary. And then there's cardiovascular, there's renal damage, there's almost or nothing in the body this thing can't hit. Kawasaki disease, it's a blood vessel disease of children, and you get it, and this is one of the things that you can get in children and in adults. And in children, you also get this so-called multiple inflammatory syndrome, which means in a small proportion they go on to become incredibly sick, a life-threatening disease. So when you say recovery, what are we recovering from? It's not just coughing, right? It's all the stuff in your body that's been perturbed. So this is slightly out of date. It says, this is for 2020. So COVID killed 3 times as many people as flu and pneumonia combined last year. And these are the rates of, shall we say, increased threat as you get older. So in terms of complications, if you're over 85, you're 13 times more likely than a young person to get the severe effects. And also you're 630 times more likely to die. So as you get older, there are more things to go wrong, basically. The symptom chart is quite interesting, what to watch for. The coronavirus, COVID-19, is nothing like a common cold. Really, there are very few symptoms in there. So you often have a runny nose and things like that. And it almost never happens with the coronavirus. The coronavirus is actually quite similar to influenza in terms of its main symptoms. So how does it get around? Well, it flies through the air with the greatest of ease. And aerosol transmission was proven actually as long ago as last August. And in fact, the safe distance is almost certainly further than the 1.5 to 2 meters everybody you see in all the signs. And it's actually probably can jump at least 4 meters, right? So the thing is you can't use that operationally in the real world, because if you said everybody's got to be 4 meters apart, look at you all, right? It's not possible to do that, okay? You can't open any restaurants or bars or anything, even under mild sort of semi-lockdown conditions. So that's been known, but no one has acted upon it. Right? The virus can jump further than you think. Also, the PCR testing is still far from foolproof. It's actually improved. We did have as many as 30% false negatives, right? Last year. The tests have actually improved a lot, but it's to do with swabbing. You have to stick a thing right up the back of your nose. It goes in a long way. And if it's not done properly, you don't get the virus out, so you can't detect it. And probably most of the problems that exist now to do with the PCR testing is either testing at the wrong time, I'll come back to that, or just not doing it properly. In the UK, the National Health Service has a completely standardised approach to this and training for this. We don't have that in Australia. Who trains people to swab? Exactly. And the whole process, so it's only the process, any process is as strong as its weakest step. So the actual swabbing process itself might be the weakest step here. And we probably need to have something a bit more standardised in Australia going down the line, despite the fact we've been lucky so far. For instance, as a perfect proof that swabbing is inefficient, the Rose Garden. Okay, so there's the Rose Garden event last year. Everybody was swabbed. In fact, it went on, I think there was 18 people in total ended up with the virus, with the infection within a week. So clearly it didn't work. The most likely person that passed it on was the guy there, who happened to be the President of the United States, okay? But I don't think we need to dwell on that. So testing, you still have to be worried about, especially if the virus is getting smarter at evading the chemistry of the test, which it might be doing. Hang on. So let's talk about this now. Children, right? There's actually an increase in, children that are infected can also get type 1 diabetes, a lifelong condition. It's a relatively small proportion, but nonetheless, it has to be very worried about this in children. As I said, it doesn't affect children so much, the earliest variants of the virus, but the B117 and the South African 1352, actually, I think, it doesn't really matter, actually look as though they can infect children more readily as well. So again, here we are in Australia, our children have been safe so far. We need to keep it that way because other virus variants may not be so sympathetic. And then you can go on and get children, if they get it, and get multiple organ system failure and also heart failure, which is really, really dramatic. I was talking to one of my colleagues at Harvard Medical School recently, and he said in the children's hospital there, they were testing all the children last year that were coming in, whatever the complaint was for, and they found 10% of all the children were testing positive, okay, of which 10% went on to get multiple inflammatory syndrome after 6 to 8 weeks afterwards. So it's still a real issue. Here are some of the variants that are kicking around, and we have different variants of concern, as they're known. And our job, of course, is to make sure that these don't get in to Western Australia and Australia in general. And there's yet another new variant of concern identified just a few days ago in the UK. Now, the UK is actually, it seems to be a criminal here because it's got lots of these variants that look dangerous. That's because they do more testing, more genetic testing than anybody on the planet. So a greater proportion of the samples that they get from patients are tested, so you're more likely to discover variants. There's probably at least 10 times as much testing that goes on in the UK as goes on in America, so there's probably hundreds of variants out there that we don't even know about yet that's already in the US population. It is a worry. What are the long-term questions? Well, do we recover from COVID-19? What is long COVID or post-COVID? All the different organs that can be affected acutely can potentially be affected long-term, and the risks for getting other diseases for those organs can also be increased. In Australia and of course other countries, we have to worry about the ethnic minorities because they may have other problems which could contribute to their risks. Certainly in the USA, Indian tribes have actually been much more badly affected than the Caucasians. That's partly because of lack of healthcare infrastructure, but there may be also biological reasons which makes them more susceptible. And then once you've been infected, what's the level of immunity that's conferred? We still don't know the answer to that. Right? How long do the antibodies last? The evidence is that they start to drop off after 6 months to a year. Okay, but the thing about immunity, it's not just about antibodies, it's also about the cells, your immune cells. And there's a whole series of white blood cells, myriads of them with all sorts of different complex immune functions, and you can train those when you're infected, you train those to fight off the virus as well. So it's not just about vaccination. Vaccination is the equivalent to getting the virus. Of course, it fools the body into thinking you've had the virus, but it's also about the cellular immunity as well. So if you've been infected, even if your immunoglobulins, your antibodies drop, you could still have a significant amount of residual immunity. And we don't know yet about the new variants in respect to their overall infectivity. This will all emerge over the next months to a year. So this gives you part of the problem. And again, it's a complicated looking graph, but it's really simple in some respects. These are different timescales of things you want to measure. So for instance, that red curve gives you the time of infection is right on the left-hand side. And then there's a band when you can find virus up the nose. And if you test too early, you don't see it. If you test too late, you don't see it. So again, that has to be thought about very carefully in relation to things like biosecurity. So, because when you test people, of course, if that band gets narrower or broader or moves, that changes your thoughts about biosecurity. The curves on the right-hand side relate to the antibody responses. And you can see it takes a long time to build that up, right? And then they drop off with time as well. So what we've been working on is something really quite different, which is looking at what we call metabolic phenoconversion, the conversion of your phenotype, your metabolic chemistry, into something that is characteristically different that's caused by the disease. So if you like, we're looking for a metabolic fingerprint pattern that says this is COVID-19, right, not something else. So the specific combination of biological, physiological responses to the presence of that pathogen. Now, that has a very different sort of dynamic to it. Firstly, biochemical changes often precede pathological changes. In fact, they almost always do. So there is a possibility of getting much earlier detection. Also, it doesn't drop off in the same way as the drop off of the virus in the nose, for instance. And it doesn't take so long to build up in the same way of the antibodies. So it probably has a much broader time window for testing. And that means, for a biosecurity point of view, that's actually a better thing. The other thing with long COVID or post-COVID syndrome, we can measure, using those same parameters, how much you've returned to normal. So if your biochemistry is not normal at the end of the process, then you're not recovered. And all the different types of pathology, the liver, the diabetes, etc., they all have different biochemical signatures. So we can look for those and we can say you're recovered for that, you're not for that, this for that, etc. And we can start to build up a completely different way of modelling recovery and get objective classification of that, which is so far extremely difficult. So what we've actually succeeded in doing so far, we've succeeded in producing multiple testing approaches which work for acute detection in the range of sort of up to about 99% sensitive to detection, which is better than PCR. But also the metabolic profile predicts how severe you're going to become as well, the severity prediction. That's a useful piece of knowledge, because if you tested somebody and said, you've got the virus, but also from your test, we know that you're going to get very sick in 2 weeks' time, you can start thinking about proactive steps for that patient in order to prepare them and maybe intervene earlier and thus mitigate against the longer-term risk. We've also filed a US patent on this because we want to try and build these tests up to regulatory standards, and that requires actually having a sort of a legal basis and a patent basis for doing that. Because ultimately, the people that take this up to regulatory standards, they're companies, right? The diagnostics companies, and they work around an IP framework. And also to use the same metrics for trying monitoring the disease long term. So here's what's our strategy. Right, we've put together a whole series of studies. Busselton study, actually, we're using as the background. What is a normal Australian like, right? Not Western Australian. Do you fit when you've recovered, do you fit the biochemical pattern of somebody the same age and who lives in the same area as you? We've got the patient journey. We feed in all the different profiles into that. And we're mixing in data from around the world to cross-check against what other people are finding. I don't want to go into very much detail on the chemistry, but we have a whole series of different technologies which we can use to open up the body and understand the different metabolic effects of the disease. So the way we look at it is they're like windows into the house, right? If you want to see what's in a house, open the window. You could go inside and have a look around, but that normally kills people if you're doing it metabolically. So what you want is a window that allows you to look in the kitchen, what's going on there, what's going on in the liver, what's going on in the brain, etc. So all our different technologies together cover a huge amount of biochemical space. And our first paper, which was published back in August, has had over 11,000 downloads. It's actually quite a successful paper, which showed this multi-organ signature of the COVID infection. Now, again, this is sort of technically looks a bit complex, but it's actually one of the simplest diagrams I could show you to give you an idea of what we actually do. And these are using mathematical, it's a type of AI, pattern recognition statistics. And basically, each of these dots is an individual. This is one of our first data sets that we did. And the green ones are all controls, right? Normal people, healthy controls. These are people who have got COVID-19 from 2 different hospitals. Each one is an individual. And you can see they're separated in a mathematical space. Now, this is based on multiple variables that have been put in. So an equation that's created with all the different variables that allows you to do a mapping of this. And then what we can do is project in people who are either COVID negative, who have some respiratory symptoms, or potentially control people where the model doesn't know the answer. And that's what's shown on the right-hand side. The grey dots, these ones here, were people who had respiratory disease, but they were COVID negative. And they're classified as being like normal. Now, they're not normal, but this model is designed to separate out normal from COVID positivity only, not other respiratory diseases, okay? And then what was really interesting is that, I'm in there as well, because I went to a conference in Italy just over a year ago, and I got COVID-19. I didn't know it. I came back. I was chronically fatigued, exhausted. I was in the control group, right, when we were doing these tests back in June, it would have been actually, and we diagnosed me as having COVID-19. I had the antibody tests, and I had COVID-19 and hadn't realised it, which is quite extraordinary. So I knew our test works, right, because it actually diagnosed me correctly. And I do have diabetes now as a result of that. I had liver failure at one stage, but that's got better. So it's a mixed bag of things. And I still have fatigue. So there are also people in there that had been classified by the swabs as negative, but when we ran the Maya tests, they were positive, and we checked the antibodies and they were positive. So our test is better than the PCR. This person here, PD, that's in there, he's a colleague of ours. He had raging COVID-19 symptoms, and it had everything in the book. And he was tested twice, negative both times, right? But we tested him, he was positive, and we did the antibodies test, and it was positive as well. Okay, so you've got to be a little bit suspicious about some of these tests, and we don't test enough, actually, even now. Then we can look at what's the difference between them. I'm not going to go into biochemistry, but we can measure all the different variables we put in. We can say things that are bigger, higher in COVID-19, things that are lower in COVID-19. And each of these have got biochemical identities, so we can pick out what we call biomarkers. These are new diagnostic markers for that disease. And the combination for COVID-19 is pretty unique. It's a weird combination of liver and brain chemistry disorders as well. So that's quite worrying in its own right. And if you look at the actual pathway, again, sorry, complicated science here, but you look at diseases that have got similarities in the biochemistry. One of them is systemic lupus erythematosus, right, which is a disease, an autoimmune disease, or certainly an immune-driven disease, which has multiple organ impacts. It causes kidney problems, liver problems, brain problems, extreme long-term fatigue. So there are similarities that are now being shown by COVID to some established diseases, which are actually not good diseases to have. These are some of our papers, including one that was out this week. We've done quite well in publishing on a lot of this stuff. The thing that actually Spinnaker funded us to do, thank you very much for your funding, right? This stuff costs a lot of money to do. Trust me, this really costs a lot of money to do this sort of work. We sent this off actually yesterday for publication. It's under peer review now. And this is looking at the recovery of patients from WA who were sampled 6 months after they'd recovered from the disease. And in fact, they hadn't really recovered, because if we look at their symptoms, 57% of people still have between 1 and 9 symptoms 6 months after being so-called recovered, or after the acute phase of the disease. But these were people who are non-hospitalised. So they represent the vast majority of the planet who've had COVID-19, and yet they still have symptoms. We're now working on the Cambridge data set, which was where we have people who are much more severely affected, to look at the percentages here. So that is profoundly worrying. And that means for Australia, there's probably 13 or 14,000 people who've had COVID that still have symptoms and still have some problems, and some maybe problems they don't know about. I will be finishing shortly if you're fidgeting about the time. So this is the sort of way we can look at it. Again, complex science. But we take those individual markers that we discovered for the disease and we say, right, in the recovered people, are you back to normal? And you can look at parameters like neuropterin is something that's inflammatory driven. It goes made by macrophages on the influence of interferons and things like that. That goes up in patients and it comes down. You're recovered. Okay, that pathology is gone. Neuroinflammatory marker, kynurenine tryptophan ratio, that goes up and goes down for most people, but there's 3 people there it doesn't. So they may have problems related to that particular pathway. And on the bottom left, there's a whole range of things where this pathway is affected, like HIV, dementia, Tourette's syndrome, dementias, disorders, all sorts of stuff in there. So this is not a good thing to have, not a good thing to have at all. And we can go through the table and pick out different features that are still abnormal in some patients and not others. And everybody, it turns out, has a different sort of personalised response, probably through time and also in terms of the extent of their total recovery. But what we've learned so far, from the mathematics, again, this complicated looking, different sort of statistics, it stands for orthogonally filtered partial least squares discriminant function analysis, if you want to know what that stands for. But it allows us to split recovered versus non-recovered reasonably well. The blue ones are so-called recovered and the green ones are healthy. You can see that for those 2 lines of blue and green, they overlap. And where they're overlapped, the people who are outside the overlap on the blue are not recovered. And that's not recovered with respect to amino acid levels and also the blood lipoprotein levels as well. So we've created actually here from WA the world's first framework for comprehensively assessing the recovery of COVID-19. I reckon that's actually quite an achievement. So I think our last paper, hopefully, again, Spinnaker funded it, is probably our best one so far. So what do we know? Okay, finishing off. We know that we can detect it by plasma phenoconversion. We think we can probably detect it by urine as well, which is much less invasive because we're starting to work on that too. We give high sensitivities and we can predict severity from early samples. We revealed a multi-system set of failures which I've been through. Those are all listed out there. And we've created a framework which we can start to understand recovery for the individual and also understanding it for the population. And at the moment for Australia there is no comprehensive program for recall of so-called recovered patients, people who have been in hospital with COVID-19. There needs to be that because some of those people probably need some medical assistance. In America, it's sort of even worse than that because this is millions of people, millions and millions of people. And many people now in the USA who've been 6 months on, 9 months on from so-called recovery, they've got lots of problems, but their health insurers won't pay for them because there is no framework for assessing it objectively as to whether this was really caused by the COVID to start with or not. We hope to be able to discover a few things that will put that right. Finally, what are we doing now? We're working on the Harvard Pediatrics. That's just starting this week. We're working on multiple different population groups to validate our methods so we can understand also the changing nature of the disease and how it works in different populations with the overall objective of having, investigating, preventing, predicting, monitoring, translating and creating clinical actionability so we can actually do something about this for the people that need it. So on that note, I'll say thank you for kindly listening, and I'd like to thank our supporters around the world and our funders, especially Spinnaker. Thank you very much.
Thank you so much, Jeremy. That was, as always, fascinating to hear these wonderful good news stories from Jeremy on a regular basis, but it's great to hear the updates. We're going to open up for a question and answer session. For people at home, we'll be recording your questions on screen, and Danny, my colleague, will be able to call out some of those questions. But I just wanted to lead with one to start with, Jeremy, is from a health perspective that's very considered and detailed. Are we paying enough attention from an economic perspective as well?
Well, there's a number of ways to answer that question. The thing that's been unique about this disease, more unique than anything I've encountered, is the medico-economic coupling of this. So because it moved so quickly, partly because of modern communications, people can fly around the world much more easily than they used to be able to do, it actually established itself very, very quickly. There was quite a lot of political denial about this, but because it established itself in multiple sites, of course, one of the first things that happened was restricting travel around the world. And the travel industry has an awful lot of connections, you know, in terms of business and how it's done. So that is still rippling through. We haven't got a solution for that. In future, almost certainly, you're going to need some sort of vaccination certificate to be able to travel anywhere. So WA has survived remarkably well because the lockdowns that we've had here, which I believe were necessary and correct, by the way, they were effective. And so the economic damage to WA has actually been really quite small. Significant to the rest of Australia, even so, because of the impact the lockdowns have. But we still have nothing like we had in Europe. So we should, you know, horrible though it is, we should be thankful the way it's turned out. But we are not safe yet. We are absolutely not safe.
It's important to remember. Okay, I'll open questions to the floor. To keep this where the research is at the moment, I'm just going to put a caution out that we probably won't be taking questions about vaccination, because that's not what the research is currently about today, and we don't feel positioned to answer that as correctly as we otherwise might. So does anybody have a question from the floor?
Yes, I'm just wondering how you see the SARS-CoV-2 virus in relation to other viruses like influenza. Do these other viruses have similar effects, or do you think this virus is a special?
Just sorry, before you answer that, I'll just repeat the question for people at home. So the question was, does this SARS-CoV virus have similarities to other known viruses at the moment, or significant differences? Is that correct?
Yeah, so the answer is yes. I mean, it's actually, you know, from a biological point of view, or chemical point of view actually, it's similar to the original SARS-CoV-1, that's the closest thing, but also MERS as well, and a number of other coronaviruses. I don't think although MERS and SARS actually did cause these systemic effects, remember they were very localized outbreaks, right? We're actually lucky that the thing that came out of Wuhan was not SARS-1. Right, if SARS-1 had gone around the world in the way that COVID-19 went around the world, we would have had a massively greater mortality, right? Because that is a much more dangerous virus. So I'm not sure if we should be thankful about that, but the important thing is that and that was 2002, 2003 was SARS, right? But even in that short time, that 20 years, the global communication, the way people move around the planet has accelerated enormously. So viruses, zoonotic, what we call emergent zoonotic threats, diseases that come from animals, can move around more quickly than ever before, until we had to shut all the airlines down last year. But if we ever open them up again, it'll be the same sort of problem. I'm actually not sure the airlines will ever go back to the way that they were before. It's an interesting problem.
Another question? Oh, sorry, I thought you had a question. No? Over here.
There's one down here.
Hi, thanks for your presentation today. Do you expect this virus to continue to have such significant health effects on people as time progresses?
So I'll just repeat that again. The question is this expected to have significant long-term consequences as time progresses and as the virus progresses? Is that correct?
Yeah, okay, it's a good question because as we know from infectious disease in general, what happens is when a new disease appears, it tends to have very, very bad effects. I mean, things like, syphilis is a really good example of a bacterial disease, right, which came from South America. In France, they call it the English disease. In England, they call it the French disease, by the way. And that was a terrible disease. It would cause the skin to fall off your bones. And we sort of acclimatized to that over a long time. So possibly we could acclimatize. This is a virus, it's rather different. But the virus hasn't finished yet. It's still sort of evolving, right? So we don't know whether it can get better or can get worse. There's a possibility it will get worse and then we will get some sort of acclimatization to it. Certainly as we approach herd immunity, difficult to get that, but when we approach herd immunity, then there will be, the overall effects will become lower. So I think in the long term, I think it'll probably be good news, but we've still got a long way to go before then.
Are we talking decades?
That's such a difficult question. We're a year into it, right? It wouldn't surprise me if it wasn't 5 years. It could be a decade. Don't know.
Hey, thanks very much for the presentation. Really quite interesting, a bit scary in many ways as well. I was reading somewhere recently where the bubonic plague is still killing several thousand people a year, and that's something most people wouldn't know, so it could be with us for a long time. I was intrigued by your comment, certainly wearing masks prevents passing it on to other people. But with the last 2 or 3 cases that have caused lockdowns within WA and Queensland and elsewhere where one person has got it, and in WA the person I think hardly didn't go not anywhere, virtually covered all of the metro area, similar in Queensland, and lived with 5 people I think, but didn't pass it on to anyone.
Well,
I'd be interested in your comments.
it's a really good question.
Sorry, I just need to repeat for the audience at home. Sorry. So there was a reflection on how these viruses can stick around for quite some time. But the question mostly pertains to a reflection on the circumstance in Western Australia recently where the virus didn't get passed on. Is that correct? And what was the circumstance around that?
So it's good I'm not a betting man, because I'd have put a lot of money on that being passed around quite a lot. I was really actually quite shocked when it didn't happen. We were expecting it. So is it that Australians are somehow magically immune? I suspect not, because we know this does affect people and it's passed on very readily in the UK and elsewhere. It is possible, and this is absolute speculation, that we are dealing with somebody who might not have been infectious when he was going about. So if the new variant actually tightened its infectivity time, it is possible that it could be more infectious when you're infectious, you know what I mean? But if you're infectious for a less long period, then it's very, depending on when you're wandering around, becomes very important. So it could have been that he was infectious before he was wandering around. As simple as that, okay? But these are important things that we need to know, but it's certainly quite mystifying, right? And we have no direct explanation for it at the moment.
Do we have any questions from home?
There's questions here, yeah.
No, none at the moment.
There's questions over there.
Thanks, Danny. Thank you, Jeremy. That was excellent, as usual. I was interested just then to hear you talk about herd immunity, and I know there's been various discussions around the world and places like that as to whether it's actually possible. Do you think it's possible?
Well, it's not a help.
The question is about herd immunity and the possibility of herd immunity.
Okay, so herd immunity, of course, is when you've got enough people in the population that they've all been infected, so they have a high level of immunity, so it doesn't, the virus is spread is much lower. The consequence of herd immunity here is having a very large proportion of your population chronically sick because of post-COVID syndrome. If you've got 57% of people who are not hospitalised who have long-term effects, do you want 57% of the whole of Australia to be ill, some of them for the rest of their lives? So the herd immunity concept from the point of view of letting the infection go nuts is insane. It cannot work. If you wanted to crush your healthcare system, that's a real good way to do it.
Into the future as well. We've got one question from the audience at home.
Sorry, the question is, do you think that COVID was around before the date previously thought?
So the question is, was it around before the date previously thought, which was late 2019? I don't think there's a specific date.
I think the jury is out on that. It is distinctly possible that it was out before then. I know there's people, certainly the Chinese would like to make it believe that was the case. It may be the case. I mean, what can happen with these things is you can have multiple jumps, right? So it could have been a random event in a market in Wuhan. It could have happened before that as well, but it didn't propagate, right? The virus has been out there, and probably in bats and maybe some other things, for some time. So there could have been a whole series of unsuccessful attempts, if you like, to jump species. So it is possible, right? But there's no question in this particular one, it came from Wuhan. Everything points in that direction.
There's a question over here in the second row.
Back to the post-COVID and concern in that space, what appeared to me early on was there's going to be people in 20 years still suffering symptoms. How is our healthcare system, our research, our finances all going to cope with that? And what do you see as problems in that area?
So the question from the audience is about the likelihood in 20 years that we're still going to have a social, financial, health impact, and how are we economically, health-wise and research-wise responding to that, and are well equipped to do it. Is that correct? Great.
The first thing we have to do is find out how big the problem is for Australia by testing it properly, and that means federal government response, funding, getting people back. And it's in people's interest to come and report back, because we can find out whether or not they're still sick, and we can probably do something about some of the things that they might be able to find. As I said, it's still, so far, Australia's so lucky, right? Only 29,000 cases. It sounds like an awful lot, but that's still not a lot in terms of the total healthcare burden of Australia. So it would put if a significant number of those people are like diabetic, it would become a significant amount, but it's not astronomical. That question asked in the United States is really quite different, or in Europe. We are looking at multi-$100 billion problems. I actually did a calculation from diabetes risk alone, the diabetes conversion alone for the United States, and it was, I did the calculation about 6 months ago, and it was $80 billion a year then just for diabetes in America, and it's probably trebled since then. Right, so these are serious. Yeah.
And just to add to that, from Spinnaker's perspective, that was one of our big questions, one of our burning questions when we made the commitment to funding this. And I think it's really significant, in Western Australia, where we are so well protected and we have been so well buffered from this due to pretty good decision making, really. Why is research into COVID being done here? And I think the really good answer to that our organisation and our board considered was we're probably better placed than anyone else in the world to actually be doing this research, because our health system isn't under a huge amount of pressure. We have the expertise here. We have some of the most impressive technology in the world. And from our perspective, we had a moral responsibility to answer that global question. But we've got a long way to go, and we need a lot of funding to do it.
So my laboratory at Imperial College London was closed for 6 months, right, after I left. Right, so I left obviously some time ago, but if I'd still been head of department there, it would not have been closed. Because again, the Imperial Laboratory has a very similar sort of capability of the one here. Actually, not quite as good.
We have the best here, don't we? It doesn't always happen. A question from the audience at home?
Yes. Is the cause of the damage to diverse organs due to inflammation or another mechanism?
Okay, so the question is whether the cause of damage to organs is from inflammation or from other causes when you've been infected.
Yes, the answer is it is almost entirely inflammation. This is a sort of a disease where inflammatory control goes out the window. People talk about cytokine storms. These cytokines control inflammatory reactions. From the work that's been done at Cambridge, people who've been infected are pretty much clear of the virus by 60 days. And anything that's going on after that is driven by your own body overreacting to the virus. And what causes one person to overreact and another person not to is still not properly understood. That may have a partially a genetic basis, but it also may be related to things like the gut microbes you have and how they affect your immune system as well.
There's a question up the back there.
The mathematical modelling that you're doing, is this based on established and recognised modelling currently in place and is deployed in other areas, or have you sort of had to uniquely develop your modelling?
So the question for people at home is around the mathematical modelling that's utilised and whether this is based on existing standards or if it's novel. Is that correct?
It is well established, but we invented quite a lot of it. So over the last 25, 30 years, we've been doing this at Imperial. So quite a lot of the modelling tools that we use were developed there. We've actually extended many of them since we've been here, but almost all of the modelling tools would be recognised statistical tools in multivariate statistics. I mean, there are hundreds of different sorts of multivariate statistical modelling tools you can use. You try and choose the right one to suit the type of data and numbers of data points that you have, the data distributions that you have. So you have to think very carefully about how you model these, because you can get wrong answers. But what we tend to do is we use multiple modelling types, maybe 3 or 4 different types, and we make sure they agree with each other. So you use what we call orthogonal mathematical solutions to make sure that they're validated.
And can I just pick up on that, because I find that a very interesting thing, something that Jeremy and I have discussed a bit, but there's still a lot to go, is this rapid thinking and this rapid evolution of novel reaction, how can we apply that to further circumstance and potentially other disease areas?
Yeah, so, well, actually, what I've shown today, I've just skimmed the surface of the science, but it's actually applicable to any sort of disease, and especially multi-system diseases. This sort of technology and approach it really lends itself to that. I mean, I think we need to remember that there are going to be other emergent zoonotic diseases. There's been about 30-something zoonotic diseases that have come out in the last 30 or so years, and they're not going to be the last by a long way. Humans live increasingly closer to animals. Right, so we get human populations 7 billion something now. It will be 10 billion very, very soon. And as there's more and more people, they get closer and closer to animals. Right, and of course, if you think about the Wuhan market, people create weird situations in biology. So, you know, if you're thinking about the Wuhan market, you've obviously got people there. You've got bats, and a pangolin comes in there as well. So a bat counts on a pangolin, and there's a person nearby that somehow gets a virus that emerges from that. That's rather a simplification. But bats don't live with people. Bats live in caves, right? And pangolins don't live in caves, and you know. So bats and pangolins never come together, and humans and pangolins. And so humans create situations where things are not biological, and that's how zoonotic diseases emerge. They jump where they would never have jumped before. And as more and more people, more and more around the world, getting closer and closer to animals, it will increase. So we've learned a lot from COVID about how to tackle zoonotic threats going down the line.
This will be my last question for today. You've mentioned gut health a couple of times throughout today. Is that being looked at as a treatment option, you know, post-infection for dealing with these sorts of things? I've heard it discussed around immunology as well. It seems to me there's something in that.
So the question's about gut health and the assessment of gut health, or the possibility of using an understanding of microbiome and gut health in treatment and assessment of the disease. Is that correct?
Yeah. So, I'm very interested in gut health. I created a centre for gut health when I was in the UK, and we've done work on microbiome for about 20 years now. So it was one of the things that was at the very top of my mind when a year ago, when we were starting to get into the COVID thing. I talked to the clinicians and I said, can we get fecal samples from these people? Christ almighty, you could not believe what the reaction was, right? So it was just a no, right? I mean, I'm not sure if it was over their head or whether it's just too much of a yuck factor in critical care. So we never got any samples. I think some groups in the East have got some samples. So that question is a really important biological question. It hasn't been answered yet. What I do know, and this is this is this week's news, is from our analysis of the follow-up patients, we can tell by the biochemistry that there has been a frame shift in the microbiome activity from the biochemicals that are in the body that are made by bacteria. And so the follow-up patients have got some new biomarkers which weren't present before in acute illness, which relates to altered function of the microbiome. The microbes that are in your gut, by the way, right, they tune your immune system all the time. Like, there's 90% all the white blood cells in your body are in the gut lining, right, talking to the bugs, right? So if you change your microbes, you actually change a lot of things that relate to your immunity. So it's a really important question. And also, as I said earlier, an important question about understanding who's going to become severe and who isn't. Okay, and I suspect there will be a microbiome answer in there somewhere.
Do we have any further questions?
Yes, just I was wondering the long...
No, wait for your microphone.
Yes, I was just wondering if the long incubation period for COVID-19 was typical of other viruses like MERS and SARS, or even earlier ones like Spanish flu and Hong Kong flu, or whether it's something special.
So the question is about the incubation period for the virus and whether it's comparable to other known viruses such as MERS and SARS. Is that correct?
Right, so I am not a virologist, so I can't give you chapter and verse on that. I think it's a bit longer than the SARS and MERS. The others tend to have quite fast incubation times, but it's very variable. All right, it really is very variable. So some people, the trouble is you never really know the moment that somebody has got the virus, right? It's because they present usually at a hospital going, or a doctor's going, I'm not very well, right? So that is just like a black hole in our knowledge. Now, Imperial College is doing, at the moment, I think, possibly the most dangerous experiment in the world. It's managed to get ethics for it. It's dosing 90 fit people with COVID-19 and is going to monitor them. And then you know the second that they have got the virus. Those questions about incubation time, infectivity, all sorts of things will be answered by that study. I just hope that they don't have any fatalities, because that would be a terrible, terrible outcome.
It's a global precedent for medical research.
Yeah, it's a challenge study, it's called.
Got a question just in the back corner.
Just going back to the cytokine storms for the multi-system organ failure, do we know if there's any link with previous allergies and anaphylaxis with that?
So the question is about cytokine storms and whether there is any correlation or relationship with known allergies. Is that correct? And I just might ask you to explain a cytokine storm.
Cytokines are proteins, right? And they're smallish proteins. There's loads of them, and they're basically to regulate immune responses by hitting receptors. So if a particular cell releases one cytokine, it goes and just talks to another cell, says start working or stop working, right? A cytokine storm is when you get an immunological response when there's a huge burst of cytokines go out and they say to the immune cells, start working now, even if the virus has gone, right? So the immune cells sort of upregulated and they attack everything, okay? And then you start to destroy your own tissues, right? So the answer, the question was about do allergies and previous allergic history affect your severity? I simply do not know the answer to that question. I've probably read 1,500 papers on COVID in the last year, and believe me, that's quite a few. But I haven't seen anything about that anywhere, but it doesn't necessarily mean that it's... And I think if it was a really important part of it, I'd probably know, right? But there are so many papers. I'm looking at Professor Yeep, do you know about that? No, he doesn't know about that, but another professor doesn't know.
And I think that's again points to the real value of this, and this research study. Did we start in about May?
I think so. Yeah.
And to think where we've come from here, we're expecting at least another 2 years research, probably a bit more.
Oh yes.
Funding dependent, of course. But hopefully we can start answering some of those questions, not just for this virus, but to give us a deeper understanding of potentially new ones. We've probably got time for one more question, if there's another one from the floor or at home. No? Very comprehensive.
I have one. Do I need the microphone or can you hear me?
I'll repeat it anyway.
Yeah, Jeremy, it's fantastic research. There's so much there. I'm going to say something about that in a second. But which part of your research, do you think there's anything that is truly world-changing there, or is it all world-changing? We've got the phenome stuff up front, which has massive implications for detection. Mm-hmm. And then we've got the framework at the back to look at recovery. I mean, this is amazing stuff.
So, just one moment. The question is about the research as a whole, from the point of detection to prediction and long-term sort of assessment of the disease. Which part is world breaking? Which part is world leading? Or is it all?
Well, I'm quite a humble person.
What's also got commercial?
Oh, yeah, I have to say something.
And what is commercial?
Okay, so in many ways it is world leading. I think the thing that's different about, there's some other superb work that's been done, including metabolic work, but the thing that's different about ours is we look at the big picture. We've got the lab which can look at everything. Most people take one sort of machine, they measure one little framework of it, one part of the disease. It's like the famous analogy is the 6 blind men on the elephant. When you put, it's a wall, or a tusk, it's a spear. All the blind men have come up with a different conclusion about what the elephant is. We can see the elephant, right, because of the way we put our technology together. So in that respect, the systems discoveries that we made are world leading, and they are influencing what other scientists are thinking about. And I think our latest paper, which still has to go through peer review, about a framework for understanding recovery, I think that will end up being a citation classic. It's right out there. So, but I am humble, really. It's my team that's good. All right.
But I was going to say, I repeat this often, and I don't know whether I should, but when we got the first peer review comments back, it was still, for me, one of the most startling reviews to read, and it was called An Overture to a Symphony. And that was back in August, and I just about fell off the chair. I've never seen an academic say something so poetic, and particularly about something so detrimental. I'm going to invite now our chairman, Spinnaker chairman Andrew Fries, just to do a closing and to thank everyone for being here.
Thank you very much. Jeremy can be humble, but I don't have to be. I know this stuff is world-class, world-leading. This is coming out of Western Australia. How good was that presentation? How insightful, how interesting, how thought-provoking, just how good. Big round of applause. Come back to thanking you about you and your team, but I'm a very proud Western Australian. I haven't lived here for 25 years, but I've come back about 7 years ago. And I'm going to tell you, when I saw some of these slides, I felt very proud to be a Western Australian, right? We had Fiona Stanley, Murdoch University, Spinnaker, Royal Perth Hospital, Harvard, Cambridge, all in the same place, right? Now, how good is that? It is truly, truly amazing. And I think we are absolutely blessed to have this Phenome Centre and Jeremy and his team here. Again, Jeremy was humble, but I don't have to be. We showed a network of Phenome Centres around the world. Well, the leader of that network is sitting here in Western Australia under Jeremy. So we are leading a global network of Phenome Centres here in Western Australia. And I just can't be proud of it. It's fantastic. And that is made possible in part by Murdoch University, a large part of Murdoch University. Thank you. Your foresight, and your funding to get this off the ground is truly inspirational. I think the light has been held under a bushel. Thank you. I'm pretty pleased with the other funders, including Spinnaker. I think Spinnaker is not well known, but in our support and our curation of various research activities, we are helping make a difference in the world through working with fantastic people and partners, such as the Phenome Centre and Jeremy and his team. And that is only possible because of all of you, right? We rely on your support, you and you out there. We rely on your support to do what we do. And I would like to just say thank you for your support, because we are doing things. And we're going to be doing more, but thank you very much. Thank you for being here today. Thank you for your support. Thank you for all you do. I'd like to acknowledge all of the researchers that are supporting all of this within the Phenome Centre and within the universities. I'd like to also acknowledge some of the dignitaries that are here today. Two of my fellow board members at Spinnaker, Sasha Bosnich and Helen Warner. Thank you too. And we're the privilege of having one of the board members from South Metro Health here, Yvonne Parnell. So thank you for being here. And thank you for all the people that I don't know that are contributing in a major way to the health system in Western Australia and what we do. Thank you one last time, and a round of applause for Jeremy and your team and all you've done. And let's get the light of this out in the world, and let's start doing some stuff. There's some game-changing things here that will just free up the world. So thank you very much.
Yep. Daddy. What's that? Yeah. Once the recording is sent, it'll be put on Facebook. Thank you. Enjoy your afternoon. Yes. Once the recording is sent. Yeah, I press recording. So be uploaded to Facebook.
I was trapped in lockdown in Melbourne.
Sometimes
But you know, I acknowledge the fantastic things that Murdoch done. Your foresight and it's awesome. It's inspirational. I really don't believe it.
Okay. As in just, you mean power down?
Obviously, yeah.
You stop recording, yeah?
Yes.